Okay, we're ready to go. So good morning, and thank you for joining us for our CGD seminar this week. It's too heavy. I have the pleasure of introducing Pedro DiNezio as our speaker this week, and today Pedro will speak on the tropical response to ocean circulation collapse. Those of you that don't know Pedro, a little bit about him. Pedro is an associate professor at the University of Colorado's Department of Atmospheric and Ocean Sciences, teaching classes on past climate change, changing environment, and including a class on scientific writing at the graduate level in his department. Prior to moving to the University of Colorado, Pedro was a researcher at NCAR as the Roll Madden visiting scientist at the University of Hawaii and at the University of Texas. You can kind of see this warmer climate perspective, and I'll give you a little bit more. Pedro has a Bachelor of Science in Mechanical Engineering from, and excuse my pronunciation, the Instituto Tecnológico de Buenos Aires, Argentina, in other words, and a master's and PhD from the University of Miami, working with Amy Clement. Their main area of research is the dynamics, predictability, and impacts of global climate fluctuations generated by the tropical oceans. Pedro also looks at the uses of numerical models and conceptual models to investigate drivers of past environmental changes that can be inferred from geological archives to form us on and improve predictions of future climate change. As in the past seminars, we will take questions from the in-person and also the online audience at the end of Pedro's talk. If you're joining us virtually, please use the Slido link to input any questions you might have. You can find the link on the YouTube page and by going to slido.com and looking up the CGD seminar. So thank you, and Pedro, turn it over to you.
Awesome. Thank you, Betty. Before I start, I want to acknowledge everyone that continues to participate in this research. Timothy Shanahan, who this project, actually this research started as a class project at UT. It was a course that Tim and I taught. And the goal was something that Betty mentioned is how can we use past climate changes to understand future climate change. And we focus on understanding Heinrich stadials, these intervals during the last ice age when we think the Atlantic overturning circulation collapsed, driving changes in the tropics, hence the title of my talk. I'm using ocean circulation collapse just to make the title shorter, and it fits in a line. But I'm referring to the AMOC there. I just don't like acronyms. And so a lot of credit goes to Tianyi, Shihun, Xian, Allison, who were students in that class, and together collaborated on this research. Some of the ideas, actually, I discussed them with David Lee a long time ago. So a lot of credit goes to David. And this research would not have been possible without the work of Masa, Yute, Matthias, Betty, and Shu, who run all these simulations that we use to understand what we see in paleoclimate data during these intervals of AMOC collapse. So I just put all these ideas together. But it was a true teamwork to get to this point. So we know from the paleoclimate record that the North Atlantic can abruptly cool. And we learned that from this Greenland ice core record that you see in blue on the top that has abrupt cooling events. So the Younger Dryas, Heinrich stadial 1, and a bunch of other Heinrich stadials, number 2 to bigger numbers. And those changes are attributed to collapses of the AMOC. And over time, the paleoclimate community discovered that these intervals coincided with large changes in the tropics. This red record from the Cariaco Basin in the Caribbean is interpreted as shifts in the Atlantic ITCC. And you can see that during Heinrich Stadial 1, which I'm picking because it's the interval that we'll be focusing on for this evaluation of models and data, coincided with a southward shift of the ITCC or much drier conditions in this part of the Caribbean, in northern Venezuela. And over time, and this is why I'm using this paper from 2013, the paleoclimate community discovered that these changes occurred everywhere in the tropics. So this is the first time, this record from the Arabian Sea is the first time that the paleoclimate community found evidence of these abrupt changes in rainfall, in tropical rainfall, away from the Atlantic. So this is the Indian monsoon. And it's interpreted as weaker. So during Heinrich Stadial 1, this record, which is a runoff record, close to the Indus River, is interpreted as a much weaker Indian monsoon. And you can see that there's a very tight relationship between every interval in which the North Atlantic cools. We see these changes in the tropics. We also have the Younger Dryas. But we're going to be focusing on Heinrich Stadial 1 in the comparison because it occurred over much more stable glacial climate conditions. So it's easier to compare paleoclimate data and simulations. I will get back to this in a bit. So climate models can simulate widespread tropical changes in response to North Atlantic cooling. And there's a long history of so-called freshwater housing simulations in which a freshwater flux is applied to the North Atlantic, the AMOC collapses, produces cooling, and then the tropics respond. And here I'm just showing results from one of these first studies by Shang and Delworth, showing large changes in the tropical rainfall to the right, showing that, yes, the tropics can respond globally to cooling of the North Atlantic. We also have theory that anticipates that the ITCZ can shift to the warmer hemisphere when there's an interhemispheric perturbation in meridional heat transports. So these results are from Sarah Kang, and with aquaplanet simulations, they applied a negative heat flux in the northern hemisphere, compensated by a positive heat flux in the southern hemisphere. The different rates, different fluxes from 10 to 30 to 60, and they produce this cooling. Here you can see the SSTs for these different runs, and that heat flux produces cooling in the northern hemisphere, warming in the southern hemisphere, and the ITCC shifts towards the warmer hemisphere. When we include continents in this type of simulations, the picture is a lot more complicated. And this is a summary of potential mechanisms in a review by Clement and Peterson from the same year. And they argue that these two mechanisms, there's one in which cooling in the North Atlantic gets to the tropics and then is propagated zonally, mainly towards the west, across the Pacific, and then into the Indian monsoon. So that's one mechanism. And then more of a zonally symmetric adjustment in which cooling of the North Atlantic influences the northern hemisphere affected by the westerlies, and then it propagates into the tropics, shifting the ITCC uniformly across the world. So we argue that there's an incomplete understanding of mechanisms influencing the global tropics, despite a long history of housing simulations, but there's very few limited use of multi-model ensembles. Models have uncertainties, and we want to consider them when we study these mechanisms whereby cooling of the North Atlantic is communicated to the global tropics. There are actually no global, or there were no global model data evaluations until this study. Some of the evaluations were regional, and there's a wealth of paleoclimate data at this point. I just showed 2 records from the tropics, but in our compilation, we use about 80, sampling the global tropics. So it's a wealth of data that needed to be used to tell which models are right, which mechanisms are right. And the last thing is, there's also very little understanding for how these responses are relevant for understanding future changes. We know the AMOC could collapse in a warming climate. How these mechanisms that applied to the past would work in the future. So I really like this study by Katinka Velomo, very recent, in which they analyze future projections and stratify them by the magnitude of the AMOC decline. So the models in which the AMOC declines by a lot, we get much bigger responses in response to greenhouse gas forcing. So these are 4 times CO2 simulations, and it includes all the responses to greenhouse gas forcings, right? Like the wet Cape weather, the patterns of warming in the tropics, in addition to the changes in the AMOC. And what you can see is that the tropical responses to greenhouse gas forcing are very sensitive to what the magnitude of the AMOC collapse. So our approach was to use a multimodal ensemble of freshwater housing simulations with one distinction, that they were performed relative to glacial conditions. So these are, the control simulation is a last glacial maximum simulation in most of them. And this is just to ensure that we have a good mean state to compare with the data. We did a model data evaluation of these simulations against changes in hydroclimate that we inferred from proxies during Heinrich Stadial 1. That interval at the end of the last ice age and the beginning of the deglaciation, in which we know, or we have convincing evidence that the AMOC collapsed. And the Greenland ice core record shows that Greenland cooled. We use rainfall-sensitive proxies, isotopic records, proxies for aridity, vegetation records that can be interpreted as rainfall changes, runoff proxies. And we use an unbiased definition of past changes. Essentially, we looked at at the sign of the change during Heinrich Stadial 1 relative to the glacial climate, so that we can compare with the changes in the models. And then we evaluated mechanisms in future predictions using CMIP3, CMIP5, and CMIP6, historical and RCP 8.5 simulations. So our ensemble, which includes 17 simulations, freshwater housing simulations, run with 8 different models. You can see CCSM3, CSM4, and CSM1 here. Force, in some cases, with different rates of freshwater forcing to produce responses in the AMOC, different reductions in the strength of the AMOC. All of them have LGM background conditions with the exception of the trace. You can see that we include the CCSM3 trace simulation with just meltwater forcing. So that one, the glacial background, the control climate is not strictly LGM, it's just the background conditions prior to when the forcing was applied, but it's close to full glacial conditions. And you can see that there's a range of rainfall responses. Those are simulations with CSM1 that I run. Those are simulations with the MIROC model. The MIROC model had 2 different states in the AMOC, 2 initial states in the AMOC under the glacial conditions, just to test what's the sensitivity to having a weaker AMOC. We know the AMOC was weaker during glacial conditions, and to see if there was a sensitivity in the response. So that's why there's a MIROC W weak and a MIROC S strong. And you can see that the patterns are similar and different at the same time. This simulation looks more like that zonally symmetric adjustment that Clement and Peterson hypothesized. So it's nice that, again, one thing to clarify, this is not a systematic evaluation or systematic evaluation of the sensitivity of the models to the forcing. It's an ensemble of opportunity. We just combine the simulations that were available. Many of them are in the Kageyama 2013 paper, which just focused on the simulations. Here, we expanded the ensemble, and we're going to compare them with paleo data. So we evaluated these simulations against the paleo data. And here I'm showing again Heinrich serial 1. There's, as I said, abundant paleoclimate records from the tropics. The responses tend to be large relative to other abrupt events. And we know it's pretty clear what the glacial conditions are. So it's easy to infer if the changes in all these locations relative to the background climate. This is the background climate for this response. And that's how we can compare the models to the data, apples to apples. So all we did was classify these anomalies as wetter, drier, or unchanged. And we compared to the models in categorical form. We've been doing these evaluations for a while, since the 2013 paper that I co-authored with Jess Tierney. So, and these are the paleo data. So that wealth of paleoclimate records that we inspected as a group, record by record, to classify those anomalies during Heinrich serial 1 into drier and change. And some of them, we classify them as unclear. We use only the records that have enough resolution to isolate, right? Paleoclimate records have different resolutions, temporal resolutions. So the ones that we could identify an anomaly for Heinrich serial 1 that was clear. We also worked only with records that the deglacial baseline or the glacial background climate was also clear. So we could compare the anomaly relative to its baseline, its control. And you can see some of the features, if you squint, that we see in the models. Drier northern hemisphere, wetter southern tropics. So we are going to interpret these patterns with help from the models. So this is a first look at the zonal mean response, since we have a theory that says that when the northern hemisphere cools and the southern hemisphere warms, the ITCC will shift to the warmer hemisphere. So the red line shows the ensemble mean, zonal mean, rainfall change, and in the ensemble with shading showing the range in the models. And you can see that it shows a shift of zonal mean rainfall to the southern hemisphere with this increased rainfall to the south and decreased rainfall to the north. We also beamed the proxy sites into these latitudes and counted how many were dry, how many were wet, and we plot the percentage on this axis. And you can see that the proxies also show more wetter conditions to the southern hemisphere, more drier conditions to the northern hemisphere. But this is not the whole story. When we look at the agreement of the spatial patterns between the proxies and the models, and this technique is that work that I mentioned, that paper that we wrote with Jess Tierney in 2013, showing that you can use this kappa estimator that can be used to quantify agreement between categorical data, so data that is in dry and change, wet conditions. And it goes from 0 to 1. So 0 means no agreement. The patterns don't match. 1 means perfect agreement. So here we compare for all these simulations the agreement between these dry, wet, and changed categories. And you can see that despite the model simulated a shift of the ITC to the southern hemisphere in the zonal mean sense, some of them can explain a lot of the structure of the patterns, and some of the simulations don't explain them at all. So now we can use the models to see if there's a relationship between this level of agreement. And again, the agreement will not be perfect. We're working with models, and we're working with paleo data that are noisy and uncertain. But this is a huge difference from 0 to 0.5. So we can compare with some quantities in the models to see what is controlling the ability of a simulation to simulate what we see in the paleoclimate data. So we compare with a reduction in the strength of the AMOC and with the magnitude of the cooling in the North Atlantic, the quantities that initiate these tropical responses in the models. And you can see that there's not a consistent relationship between the agreement and these quantities. The models show a wide range of reductions in the AMOC. If something, there's a bit of a tendency for the opposite relationship, but the hardest you bang the model, the worst it will do at simulating what we see in the paleo data. But it's not pretty consistent. And then the magnitude of cooling in the North Atlantic, there's almost no relationship to how well that simulation will explain the paleo data. Instead, we found some sort of relationship. It's not perfect, with the magnitude of cooling in the tropical Atlantic. So this is the tropical North Atlantic. And I'm going to show you the pattern in a bit. There's departures from this relationship, but all these 5 models that simulate moderate cooling in that region have better agreement. As the models simulate more strong cooling in the high latitudes, then the agreement breaks down, but there's a tendency. And I'm going to show you how different these patterns are in the simulation. So we classified the 17 simulations in the ensemble according to the magnitude of the cooling in the tropical North Atlantic. This domain as the tropical North Atlantic into the Caribbean. So all models show strong cooling in the North Atlantic, but then there's a difference in how that is communicated to the Caribbean and the tropical Atlantic. And these are the models that have a tendency to simulate better agreement based on the previous figure. So we constructed 3 sub-ensembles and took the ensemble mean and used those patterns in the rainfall patterns to compare with the paleo data now. So that process, not all the models in each ensemble show the same type of agreement, but by averaging together, we can remove maybe some errors in those sub-ensembles and capture these robust responses that are associated with this cooling in the tropical Atlantic. So this is the agreement in using that metric, that kappa estimator from 0 to 1 for the 3 sub-ensembles based on the magnitude of the cooling. So strong cooling, moderate cooling, muted cooling. Globally, proxies against simulations, all put into this categorical form. And you can see that the moderate cooling produces, on average, when we average the simulations together into these 3 groups, produces slightly higher agreement. The shading of the bars shows the statistical significance of this estimator, because as we go, I'm going to go into smaller and smaller regions, the statistical significance of the estimator goes down. So, but we're comparing the differences between these regions. When we looked into the Atlantic ITCC domain, so it's just restrict to the Atlantic tropics, we see that there's not much of a difference, particularly with the models with muted cooling. So cooling of the North Atlantic shifts the ITCC in all simulations. And that doesn't explain why this subset of models is better. It's the rest of the tropics that produces that improved agreement. And here you can start seeing how the statistical significance goes down, which is telling us that the agreement is probably even less. But we're starting to see that there's something in the rest of the tropics that these simulations are doing that best explains what we see in the paleoclimate data. So if we look at the models with moderate tropical cooling and the rainfall changes in shading and the sites from the proxies in categorical form, you can see that the agreement is striking. It's almost like everywhere you look, this sub-ensemble of the simulations will capture what we see in the proxies. If we look at the models that have strong tropical Atlantic cooling, that show less agreement, some of the match goes away, generally because the rainfall responses are excessive. A clear example is here the Amazon, where there's a lot of drying that the proxies don't support. So these models are probably doing it too much. And then we have the models with muted tropical Atlantic cooling, which show more of that zonally symmetric adjustment. And the response is structurally different from the other sub-ensembles. And they cannot explain many key features that we see in the paleoclimate data, particularly the weather signal here in Northern Australia that we see in the proxies, and that these simulations cannot produce. They also struggle simulating this weather signal all the way here in South America along the Andes. But the main reason why they did, and also here in the Western Pacific, those simulations show increased rainfall when proxies, if something, have a tendency for drying due to this record and also unchanged towards there. So we have an ensemble of models that is a lot better at capturing these patterns, and let's see why. When we focus on this response towards the Eastern Pacific and Central America, so I'm going to be comparing the simulated changes in those sites, the Caribbean, the Eastern Pacific ITCC, you can see that, again, here, the models with tropical cooling produce much higher agreement in all that domain. Same for a domain that we can define across the Pacific, where changes in the water circulation will drive rainfall changes. The models with moderate cooling produce some agreement. You can see that the proxies are a lot noisier, especially on the maritime continent, and that's why the agreement is so much lower for these models, but still statistically significant with less significance, but more statistically significant than the other type of simulations. And then when we move to the Indian Ocean, we see a bit of a similar situation in which moderate cooling in the tropical Atlantic produces better agreement, although here the strong cooling models also produce substantial agreement. So there's something going on there. If we look at what's going on in the Eastern tropical Pacific, the responses that we see in the models are quite consistent with mechanisms in the literature. Particularly a study by Champing Shea from 2008 that argue that this response occurs as we cool the Caribbean Sea, cold air is blown into the northeastern Pacific, and that weakens the north-south temperature gradient in the eastern Pacific, and it gets amplified by a west feedback, producing warming south of the equator. And this is what shifts the ITCC in the eastern Pacific. So these are the ensemble mean air surface temperature in these simulations. We're looking at surface air temperature because we didn't have a SST output for all the simulations. But the changes we checked are very close to SSTs in the simulations that we ran that we could compare. So we have this weekend north-south temperature gradient, right? It's warmer where it's cold, colder where it's warm in the background climate. Rainfall follows. And then we studied the spread in the models, comparing the cooling over the tropical North Atlantic. So all the models show some cooling and muted, and then the changes in that temperature gradient. And you can see that as the tropical Atlantic and the Caribbean cools, that gradient weakens more. So that's consistent with that theory. And then the colors indicate the magnitude of the rainfall in this box all the way south along the Andes, where we have proxies that show weather conditions during hurricane stadials. And you can see that we see a bit of a relationship, the same relationship as these two SST patterns change more, we get more weather conditions there, and that's given by this R value between the simulations. It's negative because the cooling over the tropical Atlantic is negative and the rainfall change is positive. So this is quite consistent with this theory that as we cool the Caribbean and that air is blown by the mean trade winds to the Northeast Pacific, this gradient weakens, this side of the Pacific warms, it becomes rainier, and the entire Southeast Pacific warms, increasing rainfall in these otherwise very dry regions of the tropical Andes. For the Indian Ocean, the story is, we think it's different. Recall that all the mechanisms argue that the response was communicated from the Pacific into the Indian monsoon. Following analogies of modern interannual variability, we know that during El Niño events, the Indian monsoon tends to be weaker. What we think here is that the influence is coming from the other side of the world, from the east. And we find a strong relationship between this cooling of the Arabian Sea that the models simulate and the magnitude of the changes in rainfall over India, over the Indian monsoon domain. So that's what the scatter plot is somewhat showing, although the quantities are plotted in a funky way. I'm going to walk you through that. So what we find is that there's a strong relationship with the magnitude of the Arabian Sea cooling and the drying over India. And that makes sense. When we cool the Arabian Sea, there's less moisture to be advected by the monsoon into the monsoon winds, into the monsoon domain, and the monsoon weakens. So how does the Arabian Sea cool? So here in the shaded values, I'm plotting that magnitude of the Arabian Sea cooling. And you can see that India dries more as we get these stronger values of cooling in the Arabian Sea given by the colors. So what we think is that the Arabian Sea cools in two ways. It's either cooled by cold air being blown over the Sahara from the subtropical North Atlantic, and also over Eurasia from the North Atlantic, and both contribute to this cooling. You can see that this is just cold air being blown over continents, cooling the Arabian Sea, and then weakening the monsoon. So there's two ways that this cooling can happen. But we find a strong relationship with the cooling over the tropical Atlantic too. The more tropical Atlantic cooling, the more drying over India. The scatter is explained by the magnitude of the North Atlantic cooling. So together, these two sources of cold air act to cool the Arabian Sea. And there's a lot of research showing that there's evidence that the Arabian Sea cooled during Hurricane CL1. And But there was not a mechanism explaining, or at least a model study showing how that happens. It's these two sources of cold air. But the important thing is that once we cool the Arabian Sea, we see a bit of a similar response like we see in the Eastern Pacific, that we can trigger a west feedback, and the cross-equatorial winds in the Indian Ocean, which I'm not planning here because we didn't have wind fields for all these simulations, but we checked in the ones that we ran, and you see a weakening of the cross-equatorial winds that will produce the warming across from the Indian Ocean. And when this part of the Indian Ocean warms, then the Australian monsoon strengthens, and that explains the weather conditions here. In all this plot, I'm showing annual mean values, but here in this domain, these changes are dominated by the monsoonal seasons in each hemisphere. So I think the most exciting part is the future predictions. Do we see a similar response? So I took CMIP 3, CMIP 5, and CMIP 6 simulations, historical and RCP 8.5, and looked at the magnitude of the relative warming, because now the climate is warming. But we see this pattern of relative warming, and I looked at this box and a high latitude box. The tropical box, I normalized the warming by the tropical mean warming. The high latitude box, I normalized the warming by the hemispheric warming, because again, these simulations are warming and these patterns are emerging. So here I'm plotting those two quantities, the normalized SST change in the high latitude North Atlantic, which you can see that negative values, it means actual cooling, and values less than 1, it means that that domain warms less than the northern hemisphere. Same for the tropical Atlantic, but normalized by the tropical mean warming. So 1, it means that it warms like the tropics as a whole, and less, it means that it warms less. And you can see a bit of a relationship, but there's also a lot of scatter. So it's not like these two quantities are related. So I'm going to be focusing on these two. This is my Poor's people clustering analysis. I could have done a more sophisticated analysis, but I'm going to focus on these simulations that have about the same high latitude relative warming, but a wide range of tropical warming. So these are like the strong cooling models, and these are the more muted cooling models, very much like in the hosting simulations. And when I composite those subsets of simulations, you can see a bit of the same dichotomy that we see for the hosting simulations, with that one set simulating less warming over the tropical North Atlantic, and the other set of models simulating slightly less. If you look, there's changes elsewhere in the tropics, which I think are interesting, the Southern Ocean being one. And then we can look at rainfall. So these are the same models that I showed before, but show the changes in rainfall over the 21st century. And rainfall is normalized by the magnitude of warming in each model, just to exclude any effects from different climate sensitivities or different rates of warming. So you can see that these models with strong tropical Atlantic cooling or muted warming produce much more drying over the Caribbean, maritime continent, and even West Africa. The response is stronger. We can look at them in boxes over these domains, and you can see that the stronger cooling models show much stronger drying, and even in India, a lesser increase in rainfall. We know that the Indian monsoon should strengthen under warming because of increased moisture in the atmosphere. Same for Indonesia. We can look at the other models in my clustering analysis, and these are the muted high latitude cooling. So these are akin to the models in which the AMOC doesn't collapse much. So these models are capturing the more pure greenhouse gas response, the way it get wetter, just isolating it. And you can see that there's not a big difference between the muted tropical cooling. So it's not like in these models we have a strong high latitude cooling, yet because the tropic zone cool enough, we don't get a big tropical response, especially in the Amazon and the Caribbean. And it's only when we cool the tropical Atlantic and the Caribbean is when we get that bigger response. And then we can look at the models with much stronger high latitude cooling. And you can see that those models also don't produce as much drying in these domains and comparable responses over India. So this is also probably consistent with a double pathway into India from the high latitude North Atlantic and the tropical North Atlantic. So this shows that there's a huge uncertainty in rainfall predictions coming from how the tropical Atlantic responds to high latitude cooling due to AMOC collapses in these simulations. So I want to summarize the mechanism. This is a bit of a hour variation of the Clement and Peterson 28 schematics. We have the North Atlantic that cools, west feedback communicates that to the Caribbean. The South Atlantic warms, I didn't talk too much about that. The ITCC shifts in the tropical Atlantic. Then we have the response communicated to the Pacific by the west feedback that Champin-Shea hypothesized in 28, and a lot of other papers talked about, produces the weather signal across the spine of the Andes. It communicates the signal to the Western Pacific by changes in the Walker circulation, which I did not talk about, and explains why proxies show some evidence of drying. It's not super robust. So the maritime continent, we have more work to do to understand what the proxies are telling us. And then for the Indian Ocean, we get cooling of the Arabian Sea that could be coming via two pathways. Dries the Indian monsoon. It also dries East Africa. And then, again, it gets communicated to the southern hemisphere by a west feedback. It makes the Australian monsoon stronger, and also the entire Indian Ocean warms. So the southern, the monsoon in East Africa, the southern hemisphere monsoon also strengthens. So this is our updated view of what's the global tropical response to North Atlantic cooling. So here are my conclusions. It's actually the tropical Atlantic, the key link between the AMOC collapse and the global tropics. The magnitude of the AMOC changes are not that important, nor the magnitude of the high latitude cooling. Perhaps it's important for the Indian monsoons. We're working on explaining that mechanism exactly, how those two pathways work. The response is communicated across continents within the tropics, very much like that zonally asymmetric mechanism that Clement and Peterson hypothesized. There's no evidence of a zonally symmetric adjustment, at least in this comparison against the paleoclimate data. That mechanism may work for other Heinrich steels, maybe the weaker ones. The Indian Ocean response is driven by Arabian Sea cooling, according to the simulations. There's paleoclimate evidence that the Arabian Sea was colder than the rest of the tropics during Heinrich Seal 1. And a similar mechanism seems to be at play in CMIP models, and it appears to be one of the main sources of uncertainty in projections of rainfall in a lot of places in the tropics. Not everywhere, but at least the Caribbean, the Amazon, West Africa produces much more strong drying. And in India and in Indonesia, it opposes some of the thermodynamically induced increases in rainfall. So with that, I'll stop and take any questions.
Okay, great. Thank you, Pedro. So let's open it up to questions in the room, and then Clara Desser has one online that we'll get to in a moment. Gokhan?
Yeah, thank you, Pedro. So my question was related to your first bullet. If the magnitude of AMOC changes or high latitude cooling is not really important for tropical response, how do you know to look at high latitudes North Atlantic? And what is the importance of, I guess, it looks like your perturbations were quite high, right? 0.1 and 0.2 swear drops to instigate these responses. So the actual driving mechanism may not be realistic, even though the end result might be what you are expecting. So what is the connection, I guess, with respect to high latitude changes if the hosing is really too strong to instigate this? Is there another mechanism, or why is it assumed that the North Atlantic is the instigator of the entire thing?
Should I repeat the question or no? No need. Okay.
You don't have to.
Yeah, thanks for that question, Gogan. Actually, it's a great question. I think these results almost are suggesting that as long as you cool the tropical Atlantic, you get this global tropical response. So you could do it by other mechanisms. You probably don't need an AMOC collapse to do it. Could be drying off the Sahara and blowing more dust into the tropical Atlantic. So I think it opens the door to think about other mechanisms. I mean, I'm hoping that answers your question, but thanks for that question, because it's one of the biggest conclusions that we took from this, is that, well, what if these events, I mean, there's paleoclimatic evidence that the AMOC collapse. We know from the protactinium thorium records that ventilation in North Atlantic disappeared during high-rake stadials and the younger dryas. So these, in the paleoclimate record, these changes are correlated. But yeah, it is entirely possible that if you cool the tropical Atlantic, you can excite this global response. We think that interactions with the Sahara through dust and maybe some feedback, because, well, this also dries the Sahel, so then you produce more dust. I think we should think about that.
Okay, thank you. So from online, Clara Desser asks, when you compare the models and the proxy records, are you masking the models by where the proxies are located? I noticed that the zonal mean precipitation response maximizes farther from the equator in the proxies than the models, which may reflect land-sea contrasts.
Excellent question. Yeah, the comparison is on each proxy site. We just put the model into a categories, and we look at the sensitivity of that categorization. So then there's a lot that goes into doing that until we are convinced that that categorization of the model output is not affecting the conclusion. So we explore all those agreements for different definitions of the dry, wet, and changed conditions. We spent a lot of time explaining that in the 2013 paper. And we did the same thing here. So that was one question. And yes, indeed, Clara, the proxies are mostly terrestrial. So they are capturing mainly monsoonal responses. And that's why you see that the drier, or the prevalence of drier sites in the northern hemisphere and wetter sites in the southern hemisphere, it's further away from what the model simulate, because, and I think you're right, it's because we're just focusing on the monsoonal responses, which go further away in the tropics than the more pure ITCC shifts over the ocean, which I'm showing in the zonal mean rainfall changes from the model output.
Hey, thank you. And Dan has a question?
Hi, thanks, Pedro. I had a question about, first, your decision to treat the proxy data as categorical, proxies for wetter and drier, as opposed to using some continuous scalar values. And then also whether the uncertainties of those observations made their way into your model data comparison. I guess just thinking that, as you pointed out, these are uncertain records, and you could have a relatively small drawing that might appear robust if those uncertainties were not taken into account.
That's a good question. I mean, you could do this in a lot more objective way, considering, maybe a scale, doing z-scores and getting a range of responses, and the comparison might be more fair and maybe get at the problem of the amplitude of these changes. The way we did it was more like us looking at each record, being sure that the record had enough resolution to isolate a clear signal during Heinrich Stadial. If the model was too noisy, we would discard it. If the model did not have the resolution, we did not include it in the analysis. If the baseline was not clear, we also excluded that record because we could not compute an anomaly. So yeah, I think you can do this a lot more quantitative. The definition of the anomaly relative to the baseline can get very complicated when you start having a deglaciation and so the way we did it was like by looking at these records multiple times. We spent years looking at these records since we did that class, and we kept revising them until we were sure that we trusted our interpretation of each single record. But yeah, that's a great question, and someone should do it. Maybe it's an AI problem.
Okay, so Jerry Meal has a question from online. So the key to the global response is tropical Atlantic cooling, and you said this was due to WES feedbacks arising from the North Atlantic. But the Asian of the WES feedbacks appears to be a stronger subtropical high in the North Atlantic. So what would be strengthening the subtropical high?
Good question. I didn't talk too much about why some models cool the tropical Atlantics and others don't. We don't know. I think that's the big question coming from these studies. Why is it that some models don't do this and others do? And it's more problematic in the CMIP runs probably than in other hosting ensemble. Our ensemble of hosting simulations didn't have that many simulations without the cooling. Well, actually, we didn't have that many models, but it was consistent. Like the NCAR models cool the tropical Atlantic. MyROC, other models do not. We don't know why that happens. To answer, I'm not answering Jerry's question. I don't know what's the response in the subtropical high. So I'm going to have to get back and on that question later.
Okay, great. Steve?
Yeah, going back to the Kang et al. Result that you showed originally, I'm wondering, is there no role for Southern Ocean here in understanding tropical changes in the future?
Great question. Yeah, there might be one. As you saw, at least the CMIP, the future simulations show a big difference. Oh, it's so many animations. Here, you can see that, I mean, this is the total SST pattern, right? The normalized. There's less cooling in these models, which is consistent with the response to AMO collapse. We know when the AMO collapses, the Southern Ocean warms. So some of these tropical response that we see in the hosting simulations could be coming from the Southern Ocean. So the answer is yes. We did not explore it.
Hi, Pedro. Thanks for the nice talk. I have a question about the tropical Atlantic cooling. So if we only focus on proxy SST records, do we know how cold was the tropical Atlantic during Heinrich events?
Great question. I was prepared for that one. Okay, I'm coming up the other way. Oh, these are the hosting simulations, so this is our approach at answering this question. So this is the surface air temperature change again, because that's all we have in this very coarse color scale from the best models, the models that show agreement with the proxies. And then each side shows the magnitude of cooling. And actually, yeah, the magnitude of cooling in those sites from SST records in those categories. It's really hard to compute from paleo data the actual magnitude of the cooling relative to the baseline, because even for Heinrich Stadial 1, you're starting to have the deglaciation, so you have to define a baseline. So that's our summary for, there's a lot of sites that are intriguing that show no cooling, like this one particularly. Most of the other ones are close to the coast, so they could be influenced by local coastal processes. you have all these sites from the coast of Africa that don't show as much cooling as the models. But again, you also have a lot of proxies that do show cooling. This one, I trust. It's in the open ocean, but it's close to one that doesn't show as much cooling. So this is the challenges of working with paleo data. But I would say there's evidence of some cooling. Probably not even as strong as the best models. Okay, question.
Okay, so we are at the top of the hour. So let us thank Pedro again for the seminar.
Thank you.
Thank you.